Hello everybody, today we're going to be going over a parallel lines problem at the IB Math Studies level. So the problem gives us L1, the line L1, which passes through points A, negative 3, 0.5, and B, 9, negative 3.5. So part A asks us to find the gradient of L1, okay? Now, gradient is just a fancy way to say slope, okay? And in mathematical terms, it's m. And so the way I remember slope is that it's just rise over run. Okay, conceptually I remember it like this. I have a line, goes something like this. However much it rises and goes over is how much this slope is going to be. Okay, I can calculate the rise over run anywhere on the line. Okay, it can be from all the way back here, all the way over there. It doesn't really matter as long as the proportions are the same. Okay, so I explained this conceptually first because the formula booklet, its formula for gradient can be a little bit confusing. Its formula is m equals y2 minus y1 over x2 minus x1. Notice that the rise is linked to the y values, which is of course the vertical line, and the run to the x values, which is the horizontal line. So it makes perfect sense when you look at it now. So before we get into figuring out what m is, we need to define y2, define y1, define x2, define x1. So what you want to do is you want to have x1 linked to a y1 and x2 linked to a y2. You cannot have something like x1 linked to a y3, okay? That's not legal. Or x2 linked to a y1. That's not legal either. Okay, they have to be consistent with each other. So I will define this negative 3 as x1, and of course it needs to be paired by a y1, which is a 0.5. This 9 is going to be an x2 on point B, followed by a y2 of a negative 3.5. Okay, now that that's been defined, I can plug and chug. So our m is going to be negative 3.5, plugged in as a parentheses. Every time you plug something in, you want to put it as a parentheses, mainly because, well, I'm a visual person, so it helps a lot, but also to not mess up the double negatives. So we have negative 3.5 minus 0.5, and on the bottom we have 9 minus 3. Okay, so on the top, of course, we end up with negative 4. On the bottom we have 9 plus 3, because of the double negative, 12. This simplifies to negative 1/3. So this is part A. Part B, they give us line 2, which passes through point C of 3, 1 and is parallel to L1. When we have parallel lines, they look something like this. They have the same slope, which means that they will never touch. Okay, even if it goes on to infinity, they will never touch. And as I said, they have the same slope. So m1, the slope of line 1, is going to be equal to m2, the slope of line 2. Okay, this is a property of parallel lines. So we need to determine the equation of L2. And what I suggest using here is the point slope formula, which is actually not in the formula booklet, but it is very essential to all these problems, and it's very easy to remember. It's y1 minus y equals slope of the same line multiplied by x1 minus x. Okay? Now, y1 and x1, of course, is going to be a set of points, which in this scenario we're going to use point C, defining x1 as 3 and y1 as 1. Okay, the m1 is going to be the slope, which we know is equal to the parallel line L1, which is negative 1/3. Okay, we still looking at the formula. We have two variables. We have y and x, and you might be thinking, I have two variables in the equation. How am I supposed to work with this? Usually it's only one variable. Well, you need to trust the process because this whole thing will end up with the form y equals mx plus b. Okay, where x and y are going to be variables anyway, and this is the slope-intercept form of lines. And from this, we can reach the standard form, which is what the problem is asking for here actually, which is this form. Okay, where a, b, and d are integers. In other words, they do not have fractions. Okay, now that was a lot of talking, so let's get to work. y1, as I mentioned before, is going to be 1 minus y, which is a variable. We have the slope, which is negative 1/3, times x1, which is 3, minus x. Okay, so first things first, we distribute right here the negative 1/3. On the left side, we still have 1 minus y. On the right side, we end up with negative 1 plus 1/3 x because of the double negative. Okay, we want to get y alone to reach this form right here. Okay, we get y alone first, so we do minus 1 to both sides. I combine like terms, and we end up with negative 2 plus 1/3 x. However, there's still a negative right here, so we multiply both sides by a negative. We end up with y equals positive 2 because of the double negative minus 1/3 x. Okay, and so this is the slope-intercept form. We still haven't reached the standard form yet. Okay, and although the problem asks for the standard form right away, and you could have skipped some steps and jumped to that, I like to show it this way because I don't know, not all problems ask for the standard form right away, and I feel like having it in slope-intercept form is just more versatile, more flexible. It's also more familiar. Okay, so now to reach the standard form, we need to have the whole thing equal to 0, right? And we also want to have x being positive. Okay, those are like the two general rules. So I do plus 1/3 x to both sides. We end up with y plus 1/3 x equals 2. Do minus 2 to both sides. We end up with y plus 1/3 x minus 2 equals 0. Okay, we're not quite done yet because there's a 1/3 right here. Okay, and we cannot have fractions in standard form, so we multiply the whole thing by 3. Okay, that means y is being multiplied by 3, the 1/3 x is being multiplied by 3 so that it crosses out here, the negative 2 is multiplied by 3, and for the heck of it, 0 is also multiplied by 3, but it doesn't do anything. Okay, so this whole thing is going to lead to 3y plus x minus 6 equals 0. Okay, and just to be consistent with the standard form, we want to have x on the far left side, so that would be x plus 3y minus 6 equals 0. Okay, that was really like an unnecessary detail, but just for the heck of it, just to be consistent, I guess this one is like a little bit more correct, but they're both going to get full credit. Okay, the essential thing is that you cannot have fractions, and you usually want to try to have x with a positive constant in front of it. Okay, so that is part B. And finally, for part C, we need to find the coordinates of the x-intercept of L2. Okay, now the x-intercept is going to be wherever in the line that it touches the x line. Okay, this vertical line is y and this horizontal line is x. Okay, in order to find this, we need to ask the function, when y equals 0, what is x? Okay, if we say that y equals 0, then the values that the function can give us are any along this line. Okay, we're only going to be moving sideways because we are pegging y to 0. Inversely, if we want to find the y-intercept, we would be telling if x is 0, what is y? In this scenario, the number it's going to give us is something along this line. Okay, we don't know where, but we know it's going to be along the point is going to be along the y-intercept, okay? So that's just like a more visual way and a short explanation of why we solve this problem the way we do. And so, with this information, we plug it into the formula from part B, which is here. So we end up with x, so it's 3 times 0, minus 6 equals 0. Of course, 0 times anything is going to be 0, so this whole thing just goes to 0 right away. We end up with x minus 6 equals 0, and then x equals 6. We're not quite done yet because the problem is asking for the coordinates of the x-intercept, okay? So what we need to state is 6, 0. The 6 coming from here, and the y being 0 from the explanation before, okay? That is the problem, and I hope it helped.